In physics, work is what has been accomplished by the action of a force when it acts on an object over some distance. By definition, work is the product of the force times the distance it makes an object travel along its direction. Or to say, work is the product of the magnitude of the displacement times the component of the force parallel to the displacement. In this figure, force F makes the block move from A to B. Phi is the angle between the direction of the force F and the displacement delta R. Work W is equal to the component of the force parallel to the displacement times the displacement equals F cosine phi times delta R. And this can be expressed as the scalar product or dot product of F with delta R. So work is a scalar quantity. If the angle phi is greater than or equals 0 in less than 90 degrees, the force does a positive work. If the angle phi is greater than 90 degrees and less than or equals 180 degrees, the force does a negative work. A force can be exerted on an object and yet do no work. For example, if you hold a heavy box in your hands at rest for a time, you do no work on it, though you may feel exhausted because the displacement is 0. You also do no work on a box if you carry it a distance as you walk horizontally across the floor at constant velocity, because you exert an upward force on the box equal to its weight. But this upward force is perpendicular to the horizontal motion of the box and has nothing to do with that motion. In this case, the angle between the force and the displacement is 90 degrees. Cosine phi equals 0. So the work done is 0. When dealing with work, it is necessary to specify whether you are talking about work done by a specific object or done on a specific object. In SI units, work is measured in joule. 1 joule is equal to 1 Newton meter. Scalar product of two vectors. Because vectors have direction as well as magnitude, they cannot be multiplied in the same way that scalars are. We must define what the operation of vector multiplication means. In physics, 3 ways of multiplication of vectors are useful. 1. Multiplication of a vector with a scalar, like f equals to ma. 2. Multiplication of one vector with another vector so as to produce a scalar, like work W equals to force F dot product with displacement. 3. Multiplication of one vector with another vector so as to produce another vector, like the torque tau equals to force F cross product with R, which we are going to discuss in later chapter. The scalar product. Vector A dot product with B results in a scalar C, can also be expressed by AB cosine alpha, where A and B are the magnitudes of the vectors and alpha is the angle between them. An equivalent definition is that scalar product is the product of the magnitude of one vector and the component of another vector along the direction of the first. Since A, B, and cosine alpha are scalars, it doesn't matter in what order they are multiplied. The scalar product is commutative. A dot B equals B dot A, and it is also distributed. Vector A dot parentheses vector B plus vector C parentheses equals A dot B plus A dot C. If we use rectangular coordinate components, we have A equals AXI plus AYJ plus AZK, B equals to BXI plus BYJ plus BZK, so C equals to AXBX plus AYBY plus AZBZ. In many cases, the force varies in magnitude or direction during a process. For the case of a spring attached to the wall on left and moving horizontally on a table, if we set the origin of the coordinate O at the position where the coiled spring neither stretched nor compressed, in the positive direction of x-axis is to the right. According to Hooke's law, the force exerted by the spring on the ball is proportional to x. The amount of displacement from origin O and the direction of the force is in opposite direction of the movement. F spring equals minus kx, where k is a spring constant, which is a measure of the stiffness of a particular spring. Obviously, the force is varying during the process. Another example is a rocket moving away from Earth. The work is done to overcome the force of gravity, which varies as the inverse square of the distance from the Earth's center. The figure on the right shows the path of an object in xy plane as it moves from point A to point B. We divide the path into short intervals, each of length delta Ri, delta R2, delta R3, and etc. During each small interval delta R, the force is approximately constant. So, for the ith interval, the force does work delta Wi of approximately equals Fi dot product with delta Ri. The total work done in moving the particle the total distance from A to B is a sum of all these small work elements. W is about equal to sigma of Fi dot product with delta Ri. If we subdivide the distance into a greater number of intervals so that each delta Ri is smaller, the estimate of the work done given by the sum equation becomes more accurate. If we let each delta Ri approaching 0, then we obtain an exact result from the work done. W equals the limit of sigma Fi dot product with delta Ri as delta R approaching 0. This limit is the integral of f dot dr or f cosine alpha dr from point A to point B. The symbol for the integral is an elongate S to indicate the infinite sum, and delta R has been replaced by dr, meaning an infinitesimal displacement. This integral is called a line integral. For the common expression, we have W equals fx dx integral from a to b plus fy dy integral from a to b plus fz dz integral from a to b. If there are multiple forces acting on the object simultaneously, F equals to F1 plus F2 plus F3 and so on, we have distributive equation work W equals the work done by F1 plus work done by F2 and so on. A special case is that the force is constant in the whole path. For this case, we can take the constant force out of the integral sign. The work equals the force dot product with the displacement. For work done by variable force, let us take a look at an example to see how to use the analytical methods of integral calculus to solve the problem. One end of a coil spring is fixed at point A, while another end is connected to an object of mass m, which moves on the smooth surface of a cylinder of radius r from B to C slowly by the pull of an external force F. The direction of the force is along the tangent of the half circle. The spring constant is K, and the unstretched length of the spring is AB. Determine the work done by the external force. The object moving slowly means that the net force exerted on the object is zero. F minus mg cosine theta minus kr theta equals 0. So F equals mg cosine theta plus kr theta. Work equals mg cosine theta r d theta. Integral from 0 to theta c plus kr theta r d theta integral from 0 to theta c equals mgr sine theta c plus 1/2 kr squared theta c squared. The work done by several force equals algebraic sum of the work done by the individual force. In geometrical representation, the work done by a force equals the area under the F versus X curve. Power P is defined as the rate at which work is done. Therefore, power P equals the derivative of work W with respect to time t. Since infinitesimal work element dW is equal to force F dot product with dr, and dr dt is the derivative of r with t, which is velocity v. So power P is equal to force F dot product with velocity v. The SI unit for power is watt. 1 watt equals 1 joule per second. In engineering, we often use horsepower as unit for power. 1 horsepower equals to 746 watt.